Hi, ever wondered that you wanted to learn deep learning all models at a stretch? Hi, this is Dr. Praveen Kumar from the Department of IT, Vignans University. Here I'm presenting you all the deep learning models from Perceptron to transformers. Okay, in a single shot. Blast this. Let me share the screen. Okay, now the journey starts from the perceptron. Why this perceptron? So the psychologists and the computer scientists sat together and they thought that how human brain is working. So they identified that human brain is having 8,600 crores neurons. So they planned that how I can mimic a simple neuron with mathematics. So that invented the perceptron. The first perceptron is just it takes some inputs and it multiplies with weights, and many inputs and many weights are going to be added and a bias is added, and finally it will pass through an activation function and produces some output. This was the very first idea, where here you are free to choose your weights and you are free to choose your function here. Usually in perceptron, we call it as the threshold function. With this one, the expected output you can get here. That was the very first idea of training something, or building a artificial neuron. So that equation is, this is the famous equation, f of sum of wi xi plus b y hat equal to, okay. Why I have kept this y hat is just to make you sure that okay, so this thing is going to happen in two steps. One is training, another one is inference. While training, what we do is that first we will see that what is the output this function is producing. And that output, we call it as y hat, because the original is going to be saved separately as a y and you're going to compare it. And this is the basic concept of the supervised learning. Okay, so this is the way the perceptron is designed. After that, they wanted to make it more complex network to solve the more complex problems. So they have taken multiple perceptrons and in multiple layers. That's why the birth of multi-layer perceptron came into the picture. Or so this is hidden layer 1, hidden layer 2. This is my perceptron 1, perceptron 2, perceptron 3, perceptron 4, perceptron 5. Multiple perceptrons and in multiple layers. Okay. That's why they named it as multi-layer perceptron. And see that the dense connections area, every input is connected to the all neurons at the layer 1. See, this is my x1 input passed to the layer 1s, the hidden layer 1s, perceptron 1 and perceptron 2. And this is my input 2. This is passed via weights to the both neurons or perceptrons. And x3 also passed through the both neurons of the first layer. And first layer output is again passed to the next layer. This is what called the multi-layer perceptron. Here I have written the equations. This is Z1, Z2, Z3, Z4, Z5. You just go through these equations leisurely. Okay. And ultimately we are getting the y hat here. Okay. Now we need to look into the important point that, okay, how many W's are coming and how many biases are coming. Okay, so whether there is any importance to this weights and biases or not, or W's or not. Here W's are called the weights. So for that reason, we have to compute the weights. So here our input size is 3 points, x1, x2, x3, three values we are passing as input. And our first hidden layer is containing two perceptrons or two neurons. So the weights are going to be 3 into 2 connections. Okay, 6 connections will be there per connection, one weight. So total 6 weights. And per neuron, one bias, it's going to be 2 biases. Totally 8 weights at hidden layer 1. Then hidden layer 2. So two neurons are coming, two neurons are becoming the input and two for the next layer. So 2 into 2 will be 4 weights and 2 biases, 6 neurons, 6 weights. Okay. And 2 into 1 last layer. Okay. So we are having only output layer is 1 neuron. Okay. So this one. So here I'm using my input is coming from the two neurons. So 2 into 1, 2 weights plus 1 bias for this particular neuron. So total 3 weights. Totally, if I add up 8, 6, 14 plus 3, 17 learnable parameters. I'm saying that. So simply these 17 learnable parameters are the artificial intelligence. Now the question comes that one, what do you mean by this learning? What are these learning steps? As I have told you, you are going to, your target is Y and you are expecting the network, okay, the artificial neural network to produce Y hat, which is going to be very much similar to this or very close to this Y. This is your objective function. And okay. So for that one, what we are doing is that very first time we are computing this Y hat and we are computing the loss between the original thing and the produced thing. That is, this is the output of the neuron. Okay, or we can call it as a prediction. And this Y is, we are going to call it as a ground truth. You're going to find out the difference between these two using this equation. It's need not to be this equation only. The equations will change. As of now, we'll keep it very simple. Then compute gradient by derivating the loss with respect to W. Because you got some loss and you have to reduce this loss. This is going to be your aim. When this loss becomes 0, it means that the Y hat and YR both are same. It means that the network has learned your Y perfectly with the help of the W's. It means that the W's are making this difference. So you need to tune these W's. So for that purpose, what you are doing is that, okay, so you are computing this derivating partial derivation of loss with respect to the W. So the equation is going to be, the chain equation is going to be like this: dl by dy hat into dy hat by dz into dz by dw. Once you got this gradient, okay, so with this gradient, you have to update your weights. That is the knowledge. So W new equal to W old minus learning rate into gradient. So this learning rate is an extra parameter. Okay, so this is having a lot of importance in this one. We are not going into that detail. This is going to be a brush of kind of thing. In a single shot, you wanted to learn the entire crux of the deep learning models. So that's the way we have updated this W. This entire thing I am going to call, or we are going to call it as the back propagation algorithm. So this back propagation is algorithm is going to be run for several times. We call it as a term called the epoch. So we will run it for many a times to get this Y hat is close to Y, or else the loss is going to be very much minimized. That's 0.000 something. Once you achieve this one, you can feel that one. Okay, so the network has learned the input and output mapping perfectly, right? So the important terms of this MLP is forward propagation, backward propagation, activation functions for hidden layers, activation functions for output layers, loss functions, and optimizers. I'll quickly tell you what are these things. Forward propagation, as I have told you, okay, so when I move my input from left to right once and you calculate this y hat, that's one time is called the forward propagation. Okay, and backward propagation is performing these steps, computing the loss and computing the gradient and updating the weight is called the back propagation. This is called the back propagation. Then activation function for hidden layer. As I have told you, okay, so here I'm using this F, okay, so as of now, here I have not mentioned this F's. This can be ReLU function or ELU function or tan H function or sigmoid function. These are all the mathematical functions. You need to explore these things to learn it more. And activation function at output layer. I told you here at output layer specifically, we use only two activation functions. One is sigmoid, another one is softmax. And the differences also you need to work it out. That's it. Then go for the optimizer. So here, whatever the function I have used, W old minus learning rate into gradient value. This is a simple stochastic gradient descent algorithm or gradient descent method. Here, more advanced methods came into the picture. Now the popular thing is Adam. Okay, so you need to work it out on this one to get the in detailed. So with this, we are done with the very first artificial neural network called the multi-layer perceptron. How simple it's now? Right. Then we are jumping to the next model called the convolution neural network. We use this neural network for the image data, most probably, or I can say it as for the two-dimensional data. What is the advantage you are going to get with this one? You are going to get the advantage is location invariance. It means that the image, it can be anywhere. You can able to capture the image features best way. Can't this happening with the MLP? Yes, it's not happening with the NLP because NLP works in this way. So you have to flatten the entire image this way and you need to train the image. Image is a two-dimensional information, okay, and multi-layer perceptron is working with the one-dimensional one. So there is no match. Obviously, multi-layer perceptron cannot work very well, or even if it works also, it is going to take more number of parameters. Because of that, we are going for the CNN, and even location invariance also not achieved by the MLP. Right. How this convolution operation happens? Is it again y hat equal to f of wx plus b? Yes, absolutely. The every neural network goes through or it uses y hat equal to f of wx plus b format only. So here, this is my image. Assume that, okay, so my image size is 4 cross 4. It's at 4 cross 4 or 4 cross 4 dimension matrix. Then this is submatrix. This is called the filter or kernel, whatever it may be. Okay. So it is a small matrix 2 by 2. Okay. And I'm going to consider this as weight and this is my X or input. Again, okay, so I'm going to perform the operation. The convolution operation will be like this one. Here, I'll simply show you for one thing. This 2 is multiplied with this 1 plus this 2 is multiplied with this 1. Then this 2 is multiplied with this 1 and this 2 is multiplied with this 2. So this is what I have written. So I'm going to get the Z1 value, and that Z1 value is stored into this matrix again. Okay. So the output you're going to get is 3 cross 3 matrix. Okay. So next I'm going to slide it, and I will come for the next blocks, and I will come for the next blocks. I'll perform the same operation on each and every block, left to right and top to bottom. So ultimately I'm going to get 9 values or 9 slides. So ultimately I'm going to get 9 values, Z1 to Z9. I'm going to keep them into a matrix. We are going to call it as a feature matrix or feature map. It means that this is my original image, and this original image is, with the help of this filter, I have captured the information and I am representing it in different way. You can observe that. Okay, so you have reduced the size of the image. Okay, and these are, we are calling them as the extracted features from this image, right? And ultimately, to map this one to one particular output, that's y, again wx plus b f of y is equal to f of wx plus b. Here is my x, here is my w, and whatever I perform, I'm going to pass it to the f, one equation, one activation function. It can be sigmoid, or it can be ReLU, or it can be tanh, and the output you're going to get. So now whatever the output you got is, okay, you need to pass it to the dense layer or multi-layer perceptron network. And you know that one multi-layer perceptron is a one-dimensional one. So you have to convert this 2D into 1D. This is what called the flattening. We call it as flattening operation. Whoa, so do we need to do only once this one? Not at all. You can perform, okay, so this operation several times before reaching to this particular point. It means that you can get several feature maps to capture the best feature of the image. And one more, can I use only one filter? No, you can use n number of filters to capture the n dimensional information. Because of that only, the CNN is a very powerful model to capture the information. So once you got this feature map, okay, so you're going to flatten it and you will pass it to the neural network and you will get this y hat. It means that you have done the forward propagation. And again, you need to do the backward propagation. Before doing that one, or in backward propagation, you will calculate the loss and you will calculate the gradients and you will update the weights. Wow, where are the weights? You know that in MLP, here are the weights, but where are the weights in CNN? These only the weights, these are. So randomly we are going to take initially and we are going to update them when we are performing the back propagation, so that you're going to tune these weights and you're going to get the this image, you are going to map this image to this y hat. That's it. Okay. For example, it can be, okay, so a cat image or a dog image. So image to the word called the dog you are going to map. Done with this one. So what about the parameter computation now here? Okay. So the parameter is that, okay, so we need to see that what is our filter size. Here filter size is 4. So 4 weights are there. And image channels, whether this image is an RGB or a grayscale. If it is a grayscale, you're going to have only one channel. If it is RGB, you're going to have 3 channels. So you need to check that one, whether it is grayscale or RGB. If it is RGB, you need to put 3 here. And number of filters you are going to, number of filters, how many filters here you have taken? I have taken only one. So if I have taken more number of filters, I need to use that number also here. And bias terms, one bias term for filter. Okay, so this total 4 values, you are going to use only one bias term. You are going to add that one same bias to the all values. Okay, so ultimately 4 into 1 plus 1, this is going to be, okay, so 5. These are the learnable parameters. Wow. See this, okay, so you have taken 4 into 4, 14 cells actually, but the number of parameters are 5 only here, learnable parameters, very less. If that is the case, okay, so if you use directly the multi-layer perceptron, 16 into what is going to be your hidden layer, and that many number of weights you use to get. And here we have achieved, okay, so we did it with less number of learnable parameters. Of course, this year we are talking for the only convolution operation. Again, for this multi-layer perceptron, the weights are going to be as usually you need to compute. Okay, but here the advantage we have got is that shareable parameters we got, and we have extracted the best features from the image, and we have achieved location invariance done with the convolution operation. Wow. How to know that one? Okay, so if my image size is this much and if my filter is this much, okay, so what is going to be my feature map size? Yes, there are the formulas. The first formula is I minus k plus 1, I for the image and k for the filter or kernel. And if take the example, my 4 by 4 matrix and my 2 by 2 matrix and plus 1, 4 minus 2 plus 1 is 3. It means that if I have taken 4 by 4 matrix and 2 by 2 matrix filter, then I'm going to get a 3 by 3 matrix feature map. Done with the equation. But why I need to reduce my feature map? I want that one, okay, so the feature map also to be the same size of the original image, such that I can pass that feature map again to the next layer and next layer and next layer further. Okay. So in order to do that one, we need to perform one more task called the padding. Padding is nothing but adding extra dummy layer. That is, okay, to this image, you are going to add some extra dummy layer where you are going to put all zeros. It's not going to change your image. Yes, it is for the purpose of the mathematical operations convenience. We are adding that extra layer. So the equation for the how to find the padding value, the equation for the padding value is I minus k plus 2p plus 1. So here my padding is half 0.5. Then check that one. Okay, so 4 minus 2 plus 1 plus 1, it is 4. It means that if I have added two sides a dummy layer, then I'm going to get my 4 by 4 matrix. Okay. See that if I have added a dummy layer extra here, so this will become 5 by 5 matrix. And look at this one, this equation. 5 minus 2 plus 1 equal to 4. This is I minus k plus 1 equation. So I proved that one. Okay, so by adding the padding part, okay, so I can able to produce the same dimensions of image. The feature map, that same feature map dimensions like image dimensions. Wow. One more point is there, striding. Striding in the sense I told you that one here I'm going to slide it. Okay, this is my first block and I slide to the second block. Can I skip one block so that I can move fast, or I can just surf the entire image quickly with global data, or okay, so global features? Yes, it is possible. That is what called the stride information. It tells about the sliding window of filter on image. Usually it will be 1, but we can make it any number. Wow. So my feature image size, I don't want to reduce it. If you do not reduce it, what is it you are going to achieve? Because ultimately when you make it flatten, you need to have more number of weights at the multi-layer perceptron or the dense layer. So for that purpose, you have to reduce the dimension of the feature map. So here we are using a pooling operation. So pooling is nothing but, okay, so you are going to reduce the dimension of the feature map. Usually the pooling will be, okay, so again it is going to be taken the size of the pooling matrix. Usually it will be taken 2 by 2. So what you will do is that when you take this matrix from these 4 cells, you're going to, if you take the max value, only one value, then that's called the max pooling. If you take only mean value, that's called the mean pooling. And if you take the average of this 4 and 1 value, if you take, that's what called the average pooling. So what you are doing is that when you are completely reducing the matrix. For example, if you take this 4 by 4, you are taking one value from this particular uh, sub area, that is 2, and you are taking the stride of 2 and you are jumping into this particular piece. From here you are taking the max value 2, and here at 2 max value, here at 2 max value. So ultimately you're going to extract out of this 4 by 4 matrix, you're going to get 2 by 2 matrix. So you have reduced 50% of the dimension. So this is how you can reduce the dimensions. So the equations including stride value I minus k by s plus 1 and I minus k plus 2p by s plus 1. You just have to check this one. We have done it with s equal to 1. If you put it 2, okay, so what's happening? You can see it. Wow. We are done with the CNN. Just a quick recap. What we spoke is that, okay, so many new terms came into the picture here. Convolution operation came into the picture. You need to be careful. What is convolution operation? You need to learn and you need to practice it. And what is a feature map? And what is flattening? Then the parameter computation, you need to be careful. And this formula to capture the feature map size. And what is a padding? What is stride? What is pooling? These are all the important terms in this convolution neural network. What are the popular models in CNN? So once it is developed by Jan LeCun, the hero of this era actually, Jan LeCun. Long back he developed it. Okay. So several people have extended this CNN into several layers. Okay. So VJJ 16 layers used, VJJ 19 layers used very first time, then gone with the residual networks, gone with the dense net, the UNet, mobile net, blah, blah, blah. Maybe hundreds of models came into the picture. Okay. So it was one era that, okay, so people fought like anything building on CNN. Okay. So that's about the CNN. Wow. Within no time, we are done with the second model also. Right. With this spirit, let's go to the third model called the RNN. Wow. We are done with the tabular data, that is numerical data. Fine. And we are done with the two-dimensional data, image data, done, fine. But how about the sequence data? The information which is going to be read from left to right is called the sequence data. That can be your text or your audio, your stock prices, your RNA sequence, and blah, blah, where you are going to read it from left to right to understand it. Okay, so you are going to take one sentence or one word, word by word, to understand the entire sentence. So that's about the this data, sequence data. And now the people wanted to build a model that can understand this sequential data. What is it required to understand the sequential data? It's very simple. As I have told you, when you are looking at the second word, you need to have the knowledge of the first word. When you are looking at the third word, you need to have the knowledge of the second and the first word. And like that, when you are looking at the word of n, you need to have the knowledge of the n minus 1. All words knowledge you need to have. Then only you are going to get a complete picture. This is the toughest thing. Of course, okay, so RNN has given some solution. Let us see that here. So this is folded structure. You are going to see this one. So here information is input is passed here into this neural network. Okay, this neural network is having 3 neurons. Okay, and it is learning the things parallelly. and it is producing one HT, and the same HT is passed to the neuron. Okay, so for the next input. So that is why only I wrote it here HT, and here I wrote it as HT minus 1, and here I wrote it as HT. Why I wrote here and here and here? So you need to understand that one. This is the previous state. As I have told you, when you are reading the first word, a second word, you need to have the knowledge of the first word. So assume that if this is my second word, this is my first word's knowledge. This knowledge must be added to the second word so that then only you're going to understand the meaning of these two words, right? And here the advantage is that one, you can get the output from this way and also this way. So two ways it is possible. What is the advantage of this one? I'll let you know quickly, right? If you feel that, okay, so understanding this one is difficult, I have unfolded it. So this is going to be the unfolded structure, where here you are giving the first input x1 and it is taking the h0 previous state. Of course, when this is the first one, where will be the previous state? Obviously, it won't be, but we have to show it in mathematical terms. So this is going to be something random values, right? Okay. So again, it produces the h1 and this h1 will be passed to the next. Of course, the same RNN it is. Okay. So now here H1 is ready and the next second word is came into the picture and this second word gets into inside. The first word is added with this one and it produces the knowledge of the first and second words together. Then this is my third input. And again here the 1, 2 words knowledge is there and this knowledge is added to the third word and produces the knowledge of the 3 words. Once you got this knowledge, again, you are going to pass it to the multi-layer perceptron, MLP, or we call it as a dense layer, and you will pass it, you are going to get some y hat. Why? Again, this is also f of wx plus b, y is equal to, yes, of course. Okay, this is my x, and here are we are going to have my w's. Okay, and of course, this time the equation is going to be a little bit changed. I'm going to show it to you quickly. Look at here. This is my equation. Again, this is my f of wx plus b. These two terms are same, but here we are having the previous word information. So that's going to be my ht minus 1. Whoa, whoa, what about this w? Yes. So here we wanted to learn one more extra parameter, okay, or set of parameters called the W. So here U is going to be one set of weights and W is going to be another set of weights. So here we are learning or we are using more number of weights. Of course, this is going to be a bit complex one to understand it. So, and finally, y hat equal to f of VHT. This is my MLP, multi-layer perceptron. So xt is input at t time step and ht minus 1 is previous hidden state and ht is final hidden state. As I have told you, just pause it and go through it or understand it. So here I have taken one example to make it more clear. Input data dimension I'm assuming is 1 cross 5. So why suddenly input is you're talking? Okay. So till now in images, the data was two-dimensional data. We know that it's going to be a matrix. And in MLP, the input is a scalar value. It's very fine. But now here we are talking about the text data or sequence data and how to represent a text data or sequence data. Usually text is divided into the words and each word is represented in the form of vector. This is a big subject, comes under the natural language processing. When time comes, we'll discuss that also. As of now, understand that one. Each input is a word and that word is represented as a vector of size 5. So that's going to be my 1 cross 5 and my RNN units are 3 neurons. I am using it. So How many weights are required? My U weight is needed and W weight is needed. I'll show you that one here. For the convenience, I just have tilted this image like this, right? Okay. So here are my 3 neurons. Okay. Here are my 5 input vector. So 5 into 3 will be 15 values and 3 uh, biases will be there. And this is the magic here. It is happening. So it should mingle with the previous step. That previous information is available in another 3 neurons, assume it. Okay, so that's why here I'm going to have 3 into 3 connections. Okay, so 9 connections are there, so I'm having here 9 weights. So ultimately 15 into 9 plus 3, 27 weights are there. Understanding or digesting this point is a critical thing. You just try to get this one. And here I'm giving a simple analogy. Calculating some of the n numbers, you are going to use a concept called the sum is equal to sum plus I, where every new individual value comes, that is going to be merged into this sum, and ultimately you're going to get a sum. This sum is going to give you the information of 1 to 10 values. Similarly, here it is happening. It is taking n number of inputs and it is producing single HT. This HT is responsible to capture the total essence of that input values. Wow. What's happening here? Weight sharing. Okay, same 27 weights are shared for all words in an input record. Assume that here I am passing, okay, so n number of inputs. At this point, I am passing n number of inputs. Word 1, word 2, word 3, word 4, word n. For all these things, okay, so the same 27 weights, U and the W weights are going to be there. Why? Because the weights are already having the knowledge of previous data, and the RNN's duty is to give the essence of entire sequence. Your W1 to Wn is your sequence, and that sequence comprises one knowledge or one meaningful information that has to be produced by this RNN, and that is comprised in the HT, one single vector. Wow. A single vector has to capture the 50 words of information. Seems something weird. Yes, people identified it and they have come up with the solutions also. We'll see it. Wow. What is going to happen here? Okay. So again, the same concept, forward propagation and backward propagation. When you perform this one, you're going to do this forward propagation. You got this y and again compute the loss and again compute the gradients and go back and do it and compute the gradients and update all the weights. Wow. Here, how many times you are performing, how many inputs you are giving, that many times you need to perform the weight updation, because for every input you need to update the weight. Wow. This is what called the back propagation through time, BPPT. Okay, so this what makes it is that, okay, so it makes that when you do these derivations, the gradient value becomes very tiny value or it may become very big value. These two words are called the vanishing or exploding gradient. Here gradient, you're going to get the after performing the derivations. So that derivation value or the output of the derivation, the gradient can be very small or very bigger one. If it is very small, what happens? It becomes 0. And when the gradient becomes 0, when you are trying to update your previous weight, W old equal to W new into learning rate into gradient. If the gradient becomes 0, the W new will be very much equal to the W old. So there is no weight updation. If weight updation is not there, then it means that the network is not learning anything, because the knowledge is W only. If the W's are keep on changing, it means that that knowledge is keep on updating. If the W's are not changing, It means that the knowledge is not getting updated. Right? The solutions are two solutions are provided, LSTM and GRU, long short-term memory. They thought that one, the researchers, why don't we put a temporary memory to capture that what is the essence of information? Why this temporary memory? Assume that if I have a long sequence of 50 words, which word is important, which word is unimportant, I don't know. I have to keep all the words information in simple RNN. But in long short-term memory, what they thought is that one, they wanted to maintain a long short-term memory, very lengthy short-term memory, so that this short-term memory is going to capture the important words information so that it can able to produce the better hidden state with the important information only. Wow. How to maintain this information? Okay, so it's a modification of the RNN structure, but the concept is same. Okay, so the same structure I have kept instead of writing the RNN. Okay, so I kept it as LSTM. So this LSTM is a combination of the more number of steps, that is 4 steps. Okay, so in RNN we get HT or hidden state with simple equation, but here we are going to use the 4 steps. That is, when the input is taken, it is passed through this sigmoid operation and this network will be used. And this network is called the forget network. And next network is called the input network. And next network is called the cell network. And the cell state is calculated, then this is my output network. Wow. It means that in RNN, we used to have only this one, but before this one, he has provided, okay, so this much of this many number of equations. So because of that, what happened is, okay, so a 27 parameters became 108 parameters. So LSTM is so bulky and so uh, lazy. It's not lazy. Okay, so lengthy and complex structure, more number of parameters. Okay, into 4 times. Okay, so 4 times new parameters are more parameters are required. Okay, so C stands for the cell state, which is a temporary memory, and H is hidden state, and X is the input. So usually this is shown using, okay, so this diagram. I'm sorry. Okay, so this diagram may not look okay. So beautiful. You can check it in the any website. You are going to get a better picture. Okay. So my intention is to explain you this properly. This is my input. This is my hidden state, and this is my cell state. Okay. This is my temporary memory. This is my hidden state, previous state, and this is my input. So first my input is adding with this or mixing with this hidden state, previous state, and passing through the sigmoid, and whatever the information you are getting, that's going to be with that information you are performing the dot product, or okay, so multiplication with this cell state. So cell state is going to have the previous information, so it will decide that on whether to keep that information or not. Okay, because here intelligently used the sigmoid. Sigmoid produces either 0 or 1. Okay, if it produces 0, it means that previous information is going to be erased. If it produces 1, means it is going to be keep the information. Right? Then again in next network, again the input is passed through the hidden data previous state, and again, okay, so passed through the sigmoid, it produces 1 or 0, and the same information is passed through the tan h. Now the tan h is going to have the information. Okay, and this information, that's the previous information to be there or not, how much information to be kept is identified. This is what called the input gate. That's previous information, how much I have to add it to the cell state. Okay, so here we are taking this information and we are using the addition symbol to add the information. So it means that one in CO, unnecessary information we are removing, and the information which is required we are filling it. Okay, so we are keeping it. How you are deciding it whether to put or whether to decide remove it? with the help of the sigmoid. If sigmoid produces 0, you have to remove it. If sigmoid produces 1, you can keep it. Simple. Okay. And finally, from this one, you applied the tan h and you brought the information from the temporary memory. And this information is added to the again sigmoid. And this is what? Okay. This is the RNN network. Okay. And it is producing hidden state H1. Wow. So many operations have been performed. Usually we call each step as a gate. So forget gate, input gate, cell state, and output gate. So this is the complex structures, right? Okay. Then one guy came and intelligently he has reduced, okay, so one operation. It's very much similar to this analogy. See that if you wanted to swap A and B, what is the very basic thing is that you will take a temporary variable t and t is equal to A is equal to B, and B is equal to T. So that way you're going to change it. Everybody knows it. But there is another mechanism is called the without using the temporary variable. A is equal to A plus B, B is equal to A minus B, and A is equal to A minus B. Everybody knows it. The same concept is used by this some other researcher, and he has proposed one more network called the GRU, gated recurrent unit. It's not a big change, very much similar to the LSTM, a small update to the LSTM. So instead of using the 4 number of gates, he has used that one. One is uh, update gate, and another one is reset gate. R for the reset and Z for the update gate. So again, use the sigmoid and U and WH0B. So same equation. And for the updation also same equation. And whatever the information we got it, okay, so from this reset gate, okay, so previous information is checked out here, how much has to be kept here, and whatever the h1 minus we got, okay, so that z we got, this z we subtracted from the 1, because after all sigmoid may produce either 1 or 0. So how much z is we got it here, okay, so if 1 minus 1, it is completely 0, you need to remove all the information. If it is 1 minus 0, you have to keep it everything. Wow, the same kind of this one only. A minus B and A minus B. Okay, so priorly they have added this one to get the total information. So something is the total information is this one, and he is trying to subtract it to keep it the rest of the information. And he is multiplying with this H0, that's the previous state, so that he can capture the information. And this information is added to the this H0. This is a new information. Okay, so and this is multiplied with the Z1 part. Okay, and ultimately the hidden state is produced. Here one equation is lesser than the LSTM, so the number of parameters is 3 into 27, 81 parameters. So look at this diagram, very simple diagram. Here, this is my input and this is my hidden state. I am taking it. Okay, so I'm mixing it this both and I'm passing this one. While passing very first gate is that one sigmoid and produces the information, and taking the h naught, and okay, so you are deciding that one what is the information has to be keep. So this is going to be my R part. Okay, and here again you are updating it to this hidden state. Okay, and ultimately, so you are 1 minus, you are subtracting the information from the 1, and how much you are getting that you are taking, and the new information you are taking from this R part and this X1, and using the tan H to produce the information, and you are multiplying it here, and you are adding that information to the hidden state, and you are producing this H. Previously, we used to have the temporary variable cell state, but here cell state is removed, and in that place, he has used only the hidden state and managed to get the information. Almost same result got for the GRU and LSTM, or sometimes a slight better result you got. One more variant is that, okay, so bidirectional. It can be RNN, LSTM, or GRU. Bidirectional in the sense why I have to read it from left to right, as I am a machine. So it is possible that I can read it from right to left also. Array can be read from the left to right or right to left. This is the advantage. Of course, human beings can't do it. Right. The hidden state is computed in both directions. Here I have given, okay. First, H1 is produced, from this H1, H3 is produced, and from this H2, H3 is produced. This is forward propagation. Once you got this H3, again from H3 to, okay, so you are producing H2, and from H2 to H1. It means that this H2 is the knowledge of the H3 and H2, and this H1 is the knowledge of the H2 and H3, and H1 contains the, okay, so H1, H2, H3 knowledge. So in right to left direction. So that way, the HD is calculated, okay, so they are not added, okay, so both information is used. It means that here if you have 108 parameters and here also you are going to have 108 parameters. So the parameters simply doubled completely. So ultimately RNN is a clumsy architecture and very complex architecture. LSTM is very and more number of parameters it takes. Okay. So understanding sequence is not that easy, right? Okay. So what are the different types of RNA networks? Why this topic came into the picture in the sense I showed you in RNA diagram, okay, this part, it's going, okay, so this way and also this way. So because of this reason, okay, so you are having so many types of RNA, okay, so which can be one-to-one, input one sequence and output one sequence. You give input as one sequence and you will get only one sequence as the output. And one to many in the sense input one sequence and output is many sequences. Many to one, input many sequences and output only one sequence. Many to many means input many sequences and output many sequences. What are the applications? Many to one is that, okay, so sentiment analysis and emotion recognition. It means that you're going to give a big sentence, many words you're going to give, and you wanted to find out only one sentiment, whether it is positive or negative, whether it is good or bad. So single word. So it has become many to one. Same case with the emotion recognition. You will give a big sentence and you will try to figure out what is the emotion of this sentence, whether it is happy or sad. Many to many cases, language translation or pause tag generation, parts of speech tag generation. So here what we do is that one, we'll give the input of one language and we'll expect the other language. Obviously, uh, uh, in input language also many words will be there. In output language also many words will be there. And even these words need not to be the same length. Right? Okay. So one to many, this is for the text generation. You will give simple one sentence and okay input and it produces the output. Just like, okay, so one prompt and for this prompt, okay, so it producing the one page information as like GPT. Right, okay. So these are the architecture diagrams. Very simply, I have put here. So many to one and many to many and one to many. Okay, so this is one and many outputs, and this is many and one output and many input and many output. One more simple variant. Okay, so can't I stack this RNNs? As I have told you, okay, so this output will be there where I have to use this one. You can pass that one to the next RNN layer. Right, okay. So one RNN layer's output is considered as input to the next RNN layer and so on. So here this is many to one case. So this input is passed to this first RNN layer and output is taken and passed as input to the next RNN layer and blah blah n number of RNN layers you can put and finally you're going to get your hidden state. Wow. We are done with the third model also. Wow, we started with the perceptron. We are done with the multi-layer perceptron. Then we done with the CNN, which works for the images. And we done with the RNN and its variations like LSTM and GRU and so much complex things we have done for the sequence data, right? And Encoder-decoder architectures. Okay, so this is one more architecture. So this is an architectural difference and it's not a actual model because this is a separation of the output actually. Okay, so let me take you this one. Inside of an encoder can be any model like MLP, CNN, RNN, LSTM, GRU. Similarly for the decoder. So encoder is a separate block where you can put your model. You like desired model you can put. Decoder is a block. You can put a desired model to do the task. What are the existing models are there? Autoencoder model is there. This is for the image data. Where what we do is that we do this one. See, take wx plus b. This x is my image, and you wanted to produce the same image, not the y here. So the difference is that, okay, left side you're going to have the image and right side you're going to have the image, and in middle you're going to have a reduced network or a bottleneck network, so that you wanted to capture the essence of the entire image into this particular small bottleneck layer. And with this one again you wanted to produce the image. Why you wanted to do this activity, right? I'll tell you that one. If you ask a student to learn an image by drawing it again, what will happen is that the student can able to understand the nuances, very clear points of that image, because he tried to mimic the diagram. While mimicking the diagram, he is going to learn the every curve of that image. So for that purpose only this concept is came into the picture, autoencoder. Okay, so this side image will be there and it is reduced, and from the reduced image original image is going to be produced. If you able to produce here the original image, then it means that your bottleneck is perfect. So that's the idea. Once you have done with this one, you just throw this decoder. You don't need it, okay, for this purpose. But of course, future, okay, so this is the entire required thing, right? And again, the same concept. Okay, so forward propagation and backward propagation until you get the best bottleneck. Wow. So we are done with the autoencoder part for images. Let's go for the sequence to sequence, uh, sec to sec model for sequence data. Wow. So here, what is the difference? Because there the image, okay, so I wanted to get a best representation of the image. Here also, of course, I wanted to get the best representation of the my input text. But what I will do, okay, so what I wanted to do is that I wanted to do a lot of things with the sequences. I wanted to generate the sequence or I wanted to translate the sequence. Okay, let's take here it as a, okay, so generation or the translation example. Look at this working of this one. I have passed the input and this encoder has produced, with the help of an RNN, it produced my HT, hidden state. And this hidden state is taken by this decoder model, and it starts with the SOS, a special token start of sentence. And with the help of this HT, it will produce the Y1. Okay, this Y1 can be a new word or summary, or it can be a translation of the this particular sentence, first word. Then this first word is taken as the input and it produces the new word, and it is going to take as input and it produces the next word. This kind of concept is called the auto regression. Okay, so auto regression, why we are calling it as auto regression? In the sense regression is producing a numerical value or a simple value, and here the same thing is happening. It is producing the one hidden state, and from the hidden state it is going to produce the output. So almost it is doing the regression task only automatically. So this is what called the auto regression model, sequence to sequence. Wow. Okay. What's happening in encoder side? HT equal to f of uxt plus wht minus 1 plus b. Very much same equation of the RNN, because I told you encoder is not something special. Encoder, in encoder we just kept the RNN. And decoder side, what is happening? Look at this. UHT plus WY0 plus P, where HT is from encoder and Y0 is from decoder or the special token. So here it is considering the first time the encoder information to produce the first output. Then second time, look at this here. Okay, it is producing US1. This is the state of the decoder S1. This is S1 and Y1 is this one produced output, and again it is giving B. Almost similar to the RNN. Okay, the same U, same W, same B, and it producing the S2, and you're passing it to softmax to produce the Y2. Do you have any doubt of this difference between S2 and Y2? S2 is the hidden state, and from this state, you are producing the original output Y2. This is going to be the word which we can understand. This S2 is going to be a numerical value or a vector value, which is equivalent to the word of this one. You are going to perform the softmax to produce the Y2. Okay, these are the little bit details of that one. Fine. We are done with the sequence to sequence model. Fine. Encoder is producing HT, and with the HT, decoder is producing the text. Plainly, very clear. Now here, so many modifications are coming here. Get ready to break your heads. Right. First variant is that. Okay. Why I need to depend, okay, so always on the previous state only. Why can't I consider the encoder's information also to produce the best output? Wow, shall I tell it once again? Right, okay. Here, look at this equation. Okay, so here you have only one, two elements only. But here the same elements I kept US1 and WY1. But along with this one, I kept this C also. What is this C? This C is nothing but the encoder's context vector. That is nothing but your HT minus 1 or HT part, the bottleneck layer's output. Why you are keeping this one? Look at this. Okay, I have taken a 50 words sentence, and the poor encoder crushed that information and understood it, and it produced one hidden state. Okay, and this hidden state is taken by the decoder only one time, and it has produced the first word, and it is taking that word and producing the second word. Okay, how it will understand that? Okay, so what is the relation between the first word and the second word? And this relation is to the encoder one, because assume that it is a translation, language translation. In language translation, it has to know that one. Okay, so the relation between the first language and the second language, assume it if it is English and Hindi, so English sentence and the Hindi sentence relation has to be understood. For that purpose, it is better that always look into the context vector or the hidden state which is given by the encoder. Right, okay, no problem, we'll look at that one. So that's why this equation came into the picture. Now the people said that one, looking at always a constant context vector from the encoder is a boring thing, because it's not giving any big modification or big help to produce my new word Y1. See, why always fixed context vector has to use? Can't we generate a dynamic context vector from encoder which gives more meaning to the decoder to produce the better outcome, right? Because encoder is producing one time the hidden state, then what it is doing? It's not doing anything. The same HT, we are using it every time. We wanted to give some trouble to the encoder such that the encoder can able to produce. Of course, it's not encoder. Okay, so we'll do that one. Okay, to capture the better output or the better context vector that is going to be useful to produce the next word by the decoder. Got it? Right. Okay. So that's the concept of attention came to the picture. Wow. This word is very popular word, attention. What do you mean by attention here? Attention in the sense, when I am trying to produce my first output y1 from the decoder, I wanted to know that one, what is the relation between this y1 and the context vector. Okay. And in this context vector also, which word is more suitable? Or before it is producing the y1, okay, so the state will be there now. When the state is there, this state is going to check with this context vector that, okay, so what is the relation it is having? What is going to be the best suitable word to produce the y part? Okay. For this one, okay, so some operation has to be done to produce this context vector dynamically. And for every new S state, I wanted to produce the new context vector. Wow. From where I will get this new context vector? Of course, you are having the hidden states at the encoder level. At the encoder, you are having n number of hidden state. If you have n number of words, you are going to have n number of hidden states. And when you are doing the translation, there is going to be an important word to be used. Okay, so to translate it properly, right? So that's why Bahdanu, this guy has proposed this word attention and he named it as additive attention. Okay. So here what he has done is that one, he proposed this CT part, which is a, as I have told you, dynamic context vector. CT is my dynamic context vector and YT minus 1 is output of the decoder and ST minus 1 is previous state of decoder. So in order to produce the new state at the decoder, he is going to use the dynamic context vector. Every time he is going to borrow the information from the encoder and ask that one, okay, so or try to produce the new context vector CT. Wow. How? So the CT equation is like this one. Okay, so he is going to compute one alpha. Okay, that is the attention weight. And this attention weight is used, he multiplied it with the hidden state of the uh, all hidden states of the encoder to produce the best CT. That's it. Okay. And here, before doing this one, how to compute this alpha TJ? Alpha TJ here is, okay, so compatibility score. Okay, it is computed using a simple ANN layer. He thought that one, let's put one more simple neural network in the encoder part, okay, to compute this compatibility score. Once you get this compatibility score, apply the softmax and to produce this alpha TJ, that is the attention weight. And once you got this attention weight, you are going to multiply it with the all hidden states and you're going to add it all those things to produce one context vector. This is what addition. Okay, so additive attention is said. So with the help of the neural network, this is neural network tan H W plus U. Okay, of course, there should be a bias also. I should put a plus B also. Right. So that's the way Bahdanu has proposed this mechanism to produce the context vector. Here, Bahdanu used the encoder and decoder, and every time from the encoder, he has taken the hidden states and he computed the attention weight, and using that weight he has multiplied all hidden states and summed up to produce the better context vector or dynamic context vector, right? Okay, so this is the way every time he has performed it. Okay. Then variant 3 is by Luong attention. He said that one, hey, why you have to use this neural network over there to capture that one? Why can't you just produce a dot product of the ST and HJ? This ST is nothing but the, okay, uh, state from the decoder and HJ is going to be the state of the encoder. These two states you perform the dot product. Okay, you are going to get the similarity score. Okay, so from that one, you try to produce the uh, context vector, dynamic context vector. Okay, so dot product operations is used to produce the similarity score instead of the neural network. The idea is to produce the similarity score. By this, using decoders, current state and hidden states encoder every time, that is the current state of the decoder and hidden states of the encoder. Every time new context vector is generated and it is used by the decoder to produce next state and the further output word. Okay. These are the variants, long attention and the Bahdanus attention. Of course, they lived for very short period because now the variant 4, the transformer, a breakthrough in AI, it's a blast. Okay. Vaswan is the intelligent guy who worked in Google. Okay. So at that time, okay. So he has come up with a paper called the All You Need Is Attention. So what he has done, he took the same encoder decoder sec to sec and Leong attention and made two radical changes. Okay, you need to understand this one very well. Removal of the RNN from the encoder and decoder. He said that one, why the hell you are using the RNN here? RNN is taking one by one input and it producing the hidden states H1 to HJ, and from these hidden states you are again computing the attention scores and you are generating the context vector. Why this RNN? Okay, so let's kick off this RNN and directly perform the raw words uh, dot product so that you are going to get the relation among the words. Because by doing this RNN part, what is it you are doing is you are trying to figure out the relation among the words, and that can be done through the dot product. He thought that one, right? Okay. Removal of RNN from encoder decoder, because computing hidden states is a sequential process and later computing attention score is a uh, delay process. He thought that directly perform dot product among all inputs. Directly perform dot product among all inputs to generate context vector. So why can't we do this one? Okay, so directly producing the context vector. Okay, so not context vector actually. Okay, so right, hidden state, nothing but context vector. And of course, again, the same concept by using, okay, so at the decoder level also, okay, so producing the new context vector. Okay, and he has used this concept, QKV matrices. Okay, and this is the biggest equation of era 2017. Okay, the blast. Softmax of QK transpose by root of dimension K into V. So this is the attention equation he has used. Okay. And what is the advantage here he wanted to get is that parallelization, because there is no sequence one word by word by word. He just done the dot product and dot product can be done parallelly. Dot product is nothing but matrix operation only. So we can take the help of the uh, GPU, and at the time 2017 the GPU power was came, so he wanted to take the help of the GPU so that we can produce the words very fast. Because of this only the GPT can able to produce documents by documents within seconds of time. Hats off to Vaswani's idea. Of course, Vaswani got the fame, but Long and the Bahadano, okay, so they were became hidden talented people, right? So he has used multi-headed attention. A single set of QKV learns the sentences on relation. If we use multiple sets, model can understand multiple relations at a time. So if I use QKV one set of equations or one set of weights, it can understand only single sentence or single relation. If I use multiple things, I can able to get the multiple dimension information, right? Okay. So he has used multiple QKVs. So Q, KV, VI, QI, and KI, multiple I's, and all are going to be considered the different heads. And these heads are concatenated after learning it. Again, here also the same forward propagation and backward propagation. There's no big difference. Same encoder and decoder. Of course, here, okay, so it is the Y part is nothing but producing the word. Here it is especially this transformers is developed for the purpose of language translation. Later, okay, so it has broke down into the BERT and GPT. We will look at this one into another video. The extension that is till now we are done with the pre-era of transformers. Now we have to look at into post-era of transformers, which are BERT and GPT and whatnot, LLMs, etc. Where W0 is a final weight matrix that smooths out the combined information of all heads. And he has not simply made it, okay, so simple thing, he has used positional encoding and layer normalization, feed forward neural network with ReLU and GLU. Okay, so this is the flow from the multi-layer perceptron to transformers. Wow, we did it almost within 1 hour, 8 minutes, I think so. Okay, now the point is that when from here onwards, it is starting. Wow, what is it? We have studied a 30 years of history. History is always history. Now there is no RNN, there is no LSTM, not required. This LSTM and RNN. Okay, everything is attention. Whether you take image data, whether you take audio data, whether you take text data, whatever it is, everything is transformers. Okay, and even you don't consider the data alone, they combined the data and okay, so just performed the dot product to figure out the relation among them and passed it. And only one network prevailed, that is encoder-decoder. That's it. You want it encoder, you use it encoder. You want it decoder, you can use it decoder, and you can use a combinedly encoder-decoder. That's it. Okay. And inside that encoder and decoder, no RNN, no LSTM, only the attention, even no CNN also. This the irony, or this is the sad demise or death of the all models like CNN, RNN, LSTM. Of course, for our small data and okay, so specific purposes, you can use LSTMs and RNNs, it's fine. But boldly, people are saying that one, almost all are dead. The only thing is live is encoder and decoder and transformers. Of course, transformers is a huge architecture. I haven't discussed about that one. We will get into the next video where we will start from the transformers, and from there where to go. I need to figure out this. Spend a lot of time to come up with from the scratch to the okay. So at this level, so hope you like this video. If you like it, okay, share it to your friends so that in a single hour, at a time, okay, so understanding from perceptron to transformers is not a joke. And I never seen such a video, okay, so in YouTube. So it should be useful to you. Thank you. Thank you all.